The population changes with time according to this formula. Note 5,000 and 1,000 are just constants, so really the thing that's allowing the population to change is the cos30t function. So cos starts at 1 and then goes up and down like this. And it's not a bad shout to just straight away, I reckon, try and sketch the actual function. It's going to, when t is 0, we're going to get 4,000. And then actually, as t increases, cos is going to decrease and the population is going to go up. So it's going to end up looking a little bit like this. Now we're asked to work out the maximum size of the population, so that's going to be one of these peaks. It's going to be when cos30t is actually negative because we're subtracting something. So you want to subtract the lowest thing that you can to make p the biggest that it can be. So it's going to be 5,000 plus 1,000 when cos30t is minus 1. Therefore, the maximum size will be 6,000. Work out the difference between the largest and the smallest values. Well, we've said that the largest is 6,000. The smallest is going to be when cos30t hits 1, because cos varies between minus 1 and 1. So it's 6,000 minus 4,000, and the difference between the largest and the smallest is going to be 2,000. Without giving any numerical values, describe briefly the behavior of the population over time. So I've already kind of indicated it and talked about it going up and down. Best thing to write down is to say that it will oscillate. You can say it will fluctuate, go up and down, repeat every cycle, but the best word is oscillate to describe this sort of function. The time taken for the population to return to its initial size for the first time. So it's gonna be at this bottom bit here. So at time is 0, it's gonna have its minimum point, and the next time is gonna be here. And it's gonna be, remember, cos hits 1 when t is 0, so it's when it hits 1 again, 360, but it's gonna be when 30t is equal to 360. Because basically, yeah, then this thing here will equal 360, and again, cos will be 1. So we can divide by 10, t is going to equal 12. It's going to be 12 months. So there's actually, yeah, a yearly cycle going on here we can see in this model. And turn the time on the second occasion when p is 4,500. All right, this one's going to be a bit more involved. So 4,500 must equal 5,000 minus 1,000 cos 30t. We can rearrange this to 1,000 cos 30t is equal to 500. So I've added the cos term to both sides and minus the 4,500. Divide through by 100. Therefore, cos 30t is going to equal 0.5. Cos, when does that hit 0.5? Well, we can use our calculator, but actually this is an exact trig value. It's going to be when it's 60. So when t is 60, 30t is equal to 60. Except that's going to be the first occasion on its way down. The second occasion is going to be here. 360 minus 60, so 300. Of course, feel free to do inverse cos of 0.5 and then, yeah, use the properties of cos, 360 minus the 60. And therefore, for the second time, this is what we're interested in. It's going to be 300 divided by 30. It's going to be after 10 months. And finally, a scientist observes the population, notices although it varies in a way similar to the model, the variations become smaller over time and converges to 5,000. So what this means is it's going to go up and down, but it's sort of going to get less and less. Okay, eventually look like that. So how can we change the model to take into account this population? Well, I decided to introduce an exponential term. So let p equal, right, we can't mess about with that 5,000 because we want it to converge towards that. But then I brought in an exponential term, e to the minus kt, because e to the minus kt is a negative exponential, so it's going to look a bit like that. And then, of course, I still need the cos, sorry, I'm struggling for space, but the cos 30t in there. That will create this kind of effect. Now, that is not the only answer, so I just refer now to the mark scheme. So, yeah, this is the one that I went with. Okay, maybe I should have said that k was greater than 0. I sort of implied that. It was okay if you just put in a value of k, for example. You could do things like this, raise to the power of 1 over t, or divide by t. All of these things that over time cause the term to tend towards 0. This is the fluctuating term, remember? So there'll be other possible answers as well.